probably the best bit of the show, isn't it? Algebra workout again, and this time it's the binomial theorem. Now these expressions are both quite similar. They're both of the form something plus something to the power n, a plus b to the power n. So in the first case, a is 1, b is negative x, and n is 6. The second case is just a little messier. A is 3, b is negative a half x, and n is 12. Well, the power is larger and the somethings in the brackets aren't quite as simple. It's just a sort of warning. Get the principles right on the easy example so you won't get lost on the messier ones. Now, where n is small, you may think it's easier to work out directly. For example, you can work out a plus b all squared. That's a plus b times a plus b, which in the usual way is a squared plus 2ab plus b squared. And with a bit more work, you could work out a plus b all cubed. Well, that's a plus b times a plus b all squared, which you've just worked out. It turns out to be a cubed plus 3a squared b plus 3ab squared plus b cubed. Now, doing any further calculations of that type would clearly be rather tedious, but there is a shortcut that you can use. First of all, notice the shape of these two expressions. In each case, you have expressions involving a and b, and the powers have been arranged so that the powers of a decrease. A squared, a, no a. And the powers of b increase. No b, b, b squared. In the second one, you've got a cubed down to a squared, a, no b, b, b squared, up to b cubed. And of course, in each case, the powers are multiplied by coefficients. So the real question is, what are these coefficients? Now, in the first expression, they're 1, 2, and 1. And in the second one, they're 1, 3, 3, and 1. Now, if you could work out what those coefficients were without doing the algebra, then you'd know what the expansions are. Looking for the pattern and being able to predict the coefficients is the shortcut that we're after.
You won't be surprised to learn that the shortcut we're after is well known to my electronic board here. In fact, it's already started the process. This is called Pascal's triangle, after the French mathematician Blaise Pascal. Here's the top part of the triangle, and here's how we use it. To begin with, we put ones down the edge here and down the edge here. And we fill in the other numbers as follows. The number here comes from the two ones above, 1 plus 1 giving us 2. And each number in the triangle is obtained by adding the two numbers above. For example, if you want the entry here, 1 plus 2 gives us 3. Or here, 2 plus 1 gives us 3. And let's watch while the board completes the triangle so far. Now, if you think you've seen these numbers before, well, you're right. You can see these numbers came from Francesca's manipulation of the expressions by brute force. Now, the first row corresponds to a plus b to the power 1. The second row to a plus b all squared. A squared plus 2ab plus b squared. The third row, if we can remember, to a plus b all cubed. A cubed plus 3a squared b plus 3ab squared plus b cubed. And the bottom row would appear to correspond to a plus b to the fourth. Now here's the expression for a plus b to the fourth without the coefficients. A to the fourth and the powers of a go down, a cubed, a squared, a and a term without a. And the b's go the other way, no b term here, b, b squared, b cubed, b to the fourth. And I'm suggesting that this last row gives us the coefficients that we want. This 1 here represents the 1 a to the fourth. And going along the row, the 4 would give us the 4 a cubed b. Then we would have plus 6 a squared b squared, plus 4 ab cubed, and finally plus 1 times the b to the fourth. So the fourth row gave us the coefficients. Notice that because of the way Pascal's triangle is constructed, it's symmetric about the middle, under a reflection in the central axis. So if you can calculate the first half of the coefficients, you can work out the second half quite easily. Now, Pascal's triangle is one of those lovely mathematical patterns that's a delight when you first come across it. But let's be serious. Drawing 13 rows of this pattern is really the shortcut that Francesca was looking for. We can do something about that, however. But first of all, let's check and see how the table would help us solve our problems.
Well, this Pascal's triangle has been constructed this far. So that means that I can work out a plus b to the power 6. But Alan is quite right. I'll be looking for something a little easier for the other problem. But just by reading off this row of the triangle, I can get the expansion I need. And there it is. Now, using that formula, you can answer the first of our problems, which was 1 minus x to the sixth. You replace a by 1 and b by negative x, and get 1 to the sixth plus 6 times 1 to the fifth times negative x plus 15 times 1 to the fourth times negative x squared, and so on. Now, in the end, you get this. And you'll notice that the even powers of x have a plus in front of them. That, and that, and that. And the odd powers have a minus in front of them. Now, OK, that's the first problem done. To do the second problem, we're going to use a formula for these coefficients, and Alan's going to tell us about the formula.
Yes, and this formula is going to involve factorials, so let's just revise those quickly. 4 factorial is equal to 4 times 3 times 2 times 1, and that comes to a total of 24. 3 factorial, just as another example, would give us 3 times 2 times 1, which is equal to 6. So generally, n factorial would give us n times 1 less than n minus 1 times n minus 2 times n minus 3 all the way down to 1. And by convention, 0 factorial is defined as being equal to 1. Well, how does this help us with a formula for the entries in Pascal's triangle? Here is Pascal's triangle down as far as the 6th row. And I'm going to label the rows 0 to 6. And I want some notation to label the actual entries. Let's take this one, for example. It's in the 3rd row, and we count along the row starting at 0, 0, 1, 2. The 3rd row and the 2nd position. So we label this entry 3C2. It's in the 3rd row and the 0, 1, 2nd position. So 3C2 is equal to 3. Now, just in case that's a little bit mind-blowing, let's do another example. Let's take row 5. In row 5, this element here, the 0, 1, 2nd element, would be labelled 5C2, 0, 1, 2nd element, and it's equal to 10. Now, some of you may recognise this from other branches of mathematics, but if not, don't worry. It's just a label. Now, in general, we refer to the entry in the nth row and the kth position as nck, and the general formula for that is n factorial divided by n minus k factorial times k factorial. So you can see why it was so important to revise factorials. There are 3 of them in this formula. Let's try an example. Let's try 4c3. So the n would be 4, the k would be 3, and we would get 4 factorial over 4 minus 3, which is 1 factorial, times 3 factorial, which comes in total to 4. The formula tells you each of the entries in Pascal's triangle, so you can find the coefficients in an expansion of the form a plus b to the power n, an expansion which is known as the Binomial Theorem. A plus b to the power n equals a to the n plus nc1 a to the n minus 1b plus nc2 a to the n minus 2 b squared, and on and on and on, till we end up with the final term, b to the power n.
OK, well, let's try applying this binomial theorem to a plus b to the sixth, which I did earlier by a different method, just to see if it works. So, n is 6, and we get a to the sixth plus 6c1 a to the fifth b plus 6c2 a to the 4b squared plus 6c3 a cubed b cubed, and so on until you get to b to the sixth. So you do a straight substitution there. Right, so working out some of these coefficients, you find that 6c1, that's 6 factorial over 5 factorial by 1 factorial, and that comes out to 6. 6c2, that's 6 factorial over 4 factorial times 2 factorial, and that comes out to 15. 6c3, that's 6 factorial over 3 factorial times 3 factorial, and that comes out to 20. And the rest work out in a similar way.
But before you put those values into the expansion, it's worth noticing a routine for writing out each n, c, k. Now in this case, the power we're using is n equal to 6. Now the first coefficient is always 1. And the second coefficient is always n, in this case 6. But it helps to think of that as 6 over 1, to help with a pattern that's going to follow. The third coefficient is 6 times 5 over 1 times 2. Can you see the pattern? Let's go on. The fourth would be 6 times 5 times 4 over 1 times 2 times 3. And let's just do one more. The fifth coefficient would be 6 times 5 times 4 times 3 over 1 times 2 times 3 times 4. Let's try a larger value for n now. We had 6. Let's move to n equals 12. The first coefficient is 1, always. The second is 12, which we think of as 12 over 1. The third coefficient, here's where the pattern starts, would be 12 times 11 over 1 times 2. And the fourth coefficient would be 12 times 11 times 10 over 1 times 2 times 3. And it carries on like this. But 4 terms will be enough for Francesca to make a start on the second of our 2 problems.
Certainly will be enough. Now, this is the one I called slightly messier. But in principle, we can use all the shortcuts and formulas that Alan showed us. Now, obviously, n is 12, a will be 3, and b will be a negative half x. So that's 3 to the 12th first, plus 12c1, 3 to the 11th, that's the powers going down, times a negative half x, and there's the other terms coming in, plus 12c2, 3 to the 10, power going down, minus a half x squared, that's the x's going up, and so on. So that is equal to 3 to the 12th, I'm going to work that out numerically right at the end, and this plus, this is 12 over 1 times that lot, this is 12 times 11 over 1 times 2 times that lot, and this is 12 times 11 times 10 over 1 times 2 times 3 times that lot. And now, finally, I can actually work things out. Now that's a job that involves some careful cancelling and eventually the use of a calculator. And I have done it already to save time in this programme, but it took me just a few minutes, honestly, so please don't feel put off. The answer, finally, is this.
Well, there's been quite a lot of what Francesca called messier working, but don't let that put you off.
No, and it is worth getting good at binomial expansions, because you just never know when they're going to pop up.
And that's all from us, from this edition of Algebra Workout. Since when's a binomial expansion?